So for continuity, if suppose if they are both, if these sets both are, suppose if they are both matrix spaces X as well as R infinity, then in that case for continuity we need to show that for every epsilon positive there exists delta positive such that it satisfies that property. So d of fx comma fy less than epsilon if whenever distance between x and y is less than delta. But this space is, it's not topological space, and this one it's a matrix space. So for continuity we need to show that for each epsilon positive, for continuity at a particular point, say x naught, if you need to prove continuity x naught belongs to x, then we need to show that for each epsilon positive, because here we have a matrix space, we have a distance function here. There exists not delta, but we can say there exists a neighborhood h of x naught such that whenever y belongs to that neighborhood implies distance between the fx naught and fy is less than epsilon. That's a condition for the continuity. So for each epsilon positive, there exists a neighborhood h of x naught such that whenever y belongs to h, this should imply distance between fx and fy is less than epsilon. This is same as that inverse image of open sets open actually, because this one it can be this is an open sphere actually. Distance between fx and fy, fx naught and fy is less than epsilon. It is an open sphere with center at f of x naught. So for every such open sphere there should exist a neighborhood h of x naught. So because we don't have open spheres here, it's a topological space. So this we need to show this one. F is continuous. So let x naught be any point of x, and epsilon is a positive number. Epsilon is a positive number. We show that there exists a neighborhood h of x naught such that y belongs to h. This should imply the distance between f of y comma f of x naught should be less than epsilon. Should be less than epsilon. Now, what's the distance between fy and fx naught? That is y belongs to h implies the distance between fy and fx naught is this summation n runs from 1 to infinity fn y minus fn x naught by definition of d divided by n and by definition of f also, because f of y is an infinite tuple fn y, f of x naught is an infinite tuple fn x naught by n. It's fn y by n, so it's divided by n actually here, is less than epsilon. Now since so let's prove this. For each epsilon positive there exists a neighborhood h such that we have to prove the existence of the neighborhood h satisfying this property. Now, since this f of y minus f of x naught, it belongs to R infinity, so that implies the summation n runs from 1 to infinity f and y, because f of y is an infinite tuple, okay, minus f and x naught divided by n divided by n. This is actually here, this is a distance is square whole power 1 by 2 here, less than epsilon. So this sum must be finite because it's a member of R infinity, so it's a square summable. Fy minus fx naught is an R infinity. So what's f actually? So fy is an infinite tuple, this f and y by n, and f of x naught is an infinite tuple, fn x naught by n. So fi is f1y divided by 1 comma f2y divided by 2 and so on and so forth, and f of x naught is f1 x naught by 1, f2 x naught by 2 and continue up to infinity. So that's an infinite tuple, that's also an infinite tuple, and the distance between these infinite tuple is square power 1 by 2. So but this is an R infinity, therefore this it must be square summable. That means this series is finite here. Series of squares must be finite. So since epsilon is a positive number and that series is finite, so I can find n naught such that, and it is page number 16, I can find n naught. We can choose n naught. So choose n naught in the natural number set such that the summation, so that it's actually norm of fy minus fx naught. You can use the norm here, the square, that's equal to summation n runs from 1 to infinity mod of fny minus fnx naught divided by n whole square, and this is equal to summation n runs from 1 to n naught mod of fny minus fnx naught divided by n whole square plus summation n runs from n naught plus 1 to infinity mod of fny minus fnx naught divided by n whole square. Okay, I have this, break this sum, and this n naught is chosen in such a way that this part is less than epsilon square by 2. So I can choose because the series is finite. So this is less than summation n runs from 1 to n naught mod of fny minus fnx naught divided by n whole square plus this one is less than epsilon square by 2. You can easily verify this because the series is finite. So this is always true. I can always find for each epsilon positive I can find n naught such that this holds. Now by continuity of fn for each n, since each fn is continuous, now by continuity of fn for all n equal to 1 to up to n naught, each fn is continuous and epsilon is a positive number, we can find a neighborhood. There exists a neighborhood, there exists a neighborhood Hn for each n runs from 1 to infinity, such that y belongs to Hn implies whenever y is in the neighborhood, the distance between because fn is continuous, actually fn by n is also continuous. I apply the continuity on fn by n, actually it is fn of y minus fn of x naught divided by n, fn y divided by n minus fn x naught divided by n. This square, actually it's square, okay, it is square is less than epsilon square divided by twice n naught. Epsilon square divided by twice n naught is a positive number. So for this positive number I can find a neighborhood Hn of x naught. There is a neighborhood Hn of x naught because we are discussing continuity at x naught, actually. Neighborhood Hn of x naught such that whenever y belongs to Hn, the distance between these two fn y divided by n minus fn x naught divided by n is less than epsilon square by 2n naught. Its square is here. Okay, this is the continuity of fn, as fn's are continuous functions. So now let's denote, it's page number 17, let h be is equal to intersection of h and n runs from 1 to infinity n runs of 1 to n naught, then because finite intersection of open sets is again an open set, then H is a neighborhood. H is a neighborhood of x naught because each Hn is a neighborhood of x naught. Then H is a neighborhood of x naught, and for y belongs to H, so that's a neighborhood that actually we need to show there exists a neighborhood. We need to prove that there exists a neighborhood H of x naught satisfying that property. That neighborhood is H actually. So now we prove this H satisfies that property actually. So and y belongs to H, we need to show the distance between fy minus fx is less than epsilon. So let's find that distance. Then if y belongs to H, then we need to find the distance between f of y minus f of x. Let's find the square of this distance actually, which is equal to norm of fy minus fx naught, also its square because it's the distance, square of the distance, and that's less than, which we have already proved, is less than summation n runs from 1 to n naught fny minus fnx divided by n whole square plus epsilon square by 2. Now what's this one? It's here fny minus fnx naught divided by n is less than epsilon square by 2 per its square is less than epsilon square by 2 per n naught, this square. So each term is less than epsilon square by 2 n naught, each term, and they are total, how many terms there? They are total n naught terms, and each term is less than epsilon square by 2 n naught, so it's less than n naught times epsilon square by 2 n naught plus epsilon square by 2, and that's equal to epsilon square. So this implies that distance between fy and fx naught is less than epsilon. So thus for each epsilon positive I can find a neighbor, I have a neighborhood h of y such that distance between fy and fx naught is less than epsilon whenever y belongs to h. So which implies that f is continuous, f is continuous. This function is continuous. Now we show that its inverse is also continuous. F inverse from fx to x is also continuous. Now we show that f inverse from f of x to x is continuous, is continuous. So again this one, it's a matrix space, and this is not a matrix, it's a topological space. So in that case we have to show that for every neighborhood h, there exists an epsilon positive such that satisfying that property actually. So that to prove it's continuous, we show that at continuity at x naught is a point here, x naught is a point here, given any point x naught in x. So to prove f inverse is continuous, to prove f inverse is continuous, so let's let x naught be any point in x, and let Gj be a basic open set. We prove this for only basic open sets actually, because we know that a function is continuous if and only if inverse image of basic open set is open set. So let Gj be a basic open set such that x naught belongs to Gg. Okay, so for any neighborhood Gg of x naught, we show that there exists epsilon positive, because here we can use epsilon positive because this one, it's a matrix space actually. here is epsilon positive, such that the distance between it, or you can say norm of fi minus f of x naught less than epsilon implies, this implies y belongs to gg. So this is the condition for the continuity actually here. Now since this gj, it's a second member of some order here, since gj is a second member of Pn, which is equal to gi gj, is a second member of Pn. Say Pn naught, let's denote this with Pn naught, this pair, such that x naught belongs to gi subset of gi closure subset of gj. Now let's choose epsilon. We choose epsilon. We have to prove the existence of epsilon. So we choose epsilon, a number which is less than 1 by 2 n naught. We show that this epsilon is satisfying this property. Whenever this is less than epsilon, then it should imply y belongs to gg. Let's choose this epsilon. Then this norm of then we can see that this norm of fi minus fx, we show that this, if this norm is less than epsilon, then y belongs to the neighborhood h. That's what we had to prove. For every neighborhood h, y belongs to the neighborhood gg. This gg is a neighborhood of x naught. We have to show that there exists epsilon positive, such that whenever this distance is less than epsilon, the point y should belongs to the neighborhood gg. So we assume that suppose this is less than epsilon, where epsilon is less than 1 by 2 power n naught, and we need to show that y belongs to gj. So now let's apply the definition here. What's the definition of this norm? It's summation and runs from 1 to infinity. Summation n runs from 1 to infinity. Fn y minus Fn x divided by n, its square whole power 1 by 2. So its square whole power 1 by 2. So that's less than epsilon square actually. So carrying on both sides. And what's epsilon? Epsilon is less than 1 by 2 power n naught. It's less than 1 by 4 n naught square. Or n naught square. So that implies mod of Fn naught y minus Fn naught x divided by n naught square. This must be less than 1 by 4 power n naught square, because this series, some of the squares of these terms of the series is less than 1 by 4 power n naught square. So that means each term must be less than 1 by 4 n naught square, because it's a series of positive terms, or you can say non-negative terms. So that that implies Fn naught y minus Fn naught x is less than this n naught square. This will go with this. It's less than 1 by 2. It's less than 1 by 2. Now since it's given that this x naught, it belongs to gi, it's in gi, Fn naught of x naught is here actually. It's x naught here. We are discussing the continuity at x naught actually. It should be x naught here. Okay, this is x naught actually. So x naught belongs to gi. This implies Fn naught of x naught is equal to 0, because by the condition of gi, by Urysoh's lemma actually. It's from Urysoh's lemma, because this function exists because of the Urysoh's lemma. So what is that? This is here. Okay, it should be here somewhere. This one. So for each pair Pn, I can by using lemma there is a continuous function fn from x to 0 1 such that its values on gi closure is 0 and values of gj complement is equal to 1. So here we have pair Pn naught, which is gi gj. Here Pn naught is equal to gi gj. So therefore fn naught, it's a continuous function such that fn naught maps gi closure onto 0 and it maps gj complement onto 1. So that's from Urysoh's lemma. Fn naught gj complement is 1. So x naught belongs to gi. It means that it is also in gi closure, but on gi closure its value is 0. So this one is 0, which implies that mod of fn x naught must be less than 1 by 2, because this one is 0. But it also implies that x is not in gj complement, because for if x is in gj complement, then its value must be equal to 1, but its value is less than 1 by 2, so it cannot be 1. For if x is in gj complement, then fn naught of x must be equal to 1, but fn naught of x is less than, it's x naught here, sorry, fn naught of x naught is less than 1 by 2, so that means x naught cannot be in sorry, it's here actually y, because this is not 0, this one is 0, fn naught of x naught is 0, so it's y here actually, y. So fn naught of y is less than 1 by 2, so it means that y cannot be in, this is y cannot be in gj complement, because for if y is in gj complement, then fn naught of y must be equal to 0, but fn naught of y is less than 1 by 2, so that means y is not in gj complement, which implies y belongs to gj. So thus for every neighborhood gj of x naught, I can find epsilon positive such that whenever norm of fy minus fx is less than epsilon, implies y belongs to gj complement, which implies f inverse from fx to x is continuous. So that means so therefore f from x to f of x, which is a subset of R infinity, is homeomorphism. But f of, so that means x is actually homeomorphic to f of x. So but f, so this x is homeomorphic to f of x, but f of x is a subset of R infinity, therefore it is a matrix space. R infinity is a matrix space, and it means that x is also a matrix space, because whenever we have suppose we have a homeomorphism between a topological space X and a matrix space Y. Y is a matrix space, X is a topological space. Then one can easily define a metric on X such that the topology generated by that metric is same as the topology on X. So whenever we have homeomorphism, if X is homeomorphic to Y, Y is a matrix space, X is a topological space, then we can always define a metric on X such that the topology generated by that metric is the same as the topology on X. So that means this X is matrixable. So here X is homeomorphic to f of X. This f of X, it's a matrix space, so that means X is matrixable. So that's the end of the theorem. Now I want to mention one point here, that is where I have defined it at page number 5. You can see in this lecture at page number 5, where I have defined a1 is equal to x belongs to f such that f1 x less or equal to minus 1 by 3 into 2 by 3, and b1 is equal to x such that f1 x greater or equal to minus 1 by 3, 2 by 3. It's not minus 1 by 3, it's here just 1 by 3 into 2 by 3, not minus 1 by 3. Okay, and one more thing that I want to mention here, I have written at page number 6 that this f2 is a function from x to minus 1 to 1. It's not from x to minus 1 to, it's from f. Okay, it's from f to minus 1 to 1. So thank you. That is the end of this theorem, Urysoh is embedding.